Calc AB 2012 multiple choice questions that are kind of all derivatives, limits, and about continuity. I'm just going to walk you through the solution guide. It looks like number one is just a product rule, right? It defines the function as x times sine x, and then asks for dy dx, which is just the derivative. So I use the product rule, right? The derivative of uv is uv prime plus vu prime, and there's symmetry there. It doesn't really matter what you call u and what you call v. This next one asks for when is the function increasing? The function is going to increase when it has a positive derivative. So I took the derivative, I factored it, I did a sign chart, I found where the derivatives were 0 at negative 10 and 10, and then I showed that the derivative was negative, positive, and negative. Well, if I want to know when the function's increasing, that's the interval where the function or the derivative is positive, so negative 10 to 10. This is just me taking the derivative of a function. It says f prime of 1, so I just took the derivative of 7x and negative 3 and the natural log. Remind you that the derivative of the natural log is 1 over u times u prime. In this case, it's just 1 over x. And then I evaluated it at 1. This next one, just kind of looking at this, it says which of the following is false. If you look at 2, there is a limit at 2, but it's not continuous here. There's a limit at 3, it's continuous at 3, it's not differentiable at 3. And then at 4, there's not a limit, of course it's not continuous, and of course it's not differentiable. And so, which of the following statements is false? There is not a limit at 4, there's a jump, so that C is false. This is kind of chain rule with a little power rule and a trig rule in there. So I'm going to take the derivative of this thing, I'm going to bring the 5 down, decrease the power by 1, and then I'm going to multiply by the derivative of the inside. The derivative of the inside is going to be a 3x squared, and then the derivative of negative cosine is going to be positive sine. I want it to be continuous, and I want it to be continuous, meaning I need this limit as x approaches to be equal to k. So if I just find the limit here, I can just make k that same thing, and then my limit will equal my function. And I know that the limit of the top is 5 when I let x equals 2, so then I just need k to be 5. Then it'll be nice and connected. Which of the following statements is true? Well, if you know this graph, and again, it's kind of like an absolute value graph, so it looks like a v, and that square root kind of just bends it. It is going to be continuous, but it is not going to be differentiable. The slopes are definitely not the same at x equals 2. And again, the x minus 2 is what shifted it over. This next one is a composite function. You can do this in a variety of ways. It's asking you to find the derivative of f of g. So just take the g, meaning 3x minus 2, and put it in for x, which I did here. And then I took the derivative, and I took the power rule. Bring the half down, decrease the power by 1, and then I multiplied by the derivative of the inside. And then, of course, I evaluated it at 3. Okay, this one I'm asking you to compare like h prime, and h double prime, and they define h as the integral of f. So what you're looking at, if h is the integral of f, then what you're looking at really is the derivative of h, right? H prime and f are the same thing. And so if we look at h of 6 would be the area, and the area from 0 to 6 is this big negative area. So h of 6 is negative. H prime of 6 is really 0 because that's the same thing as f of 6. And then h double prime of 6 is the same thing as f prime of 6, which is the slope, which is positive. So we have a negative area, a 0 value, and a positive slope. And so we say this. The area is negative, the value is 0, and the slope of the function given is positive. And so that's the correct order. So this is just a little calculus, right? Calculus / physics problem. They give you x of t, which is like a horizontal position function, and they want to know when it's at rest. So go ahead and take a derivative, x prime. In that case, that'd be like dx dt or v subscript x, and then I just found out where it was equal to 0, and I solved for that time. Right? That's the time when x prime is 0, which means it's at rest because it's only moving along the x-axis. This is the definition of the derivative, right? Limit of f of x plus h minus f of x over h. And you recognize that this guy right here is really asking you to take the derivative of the natural logarithm at 4. Again, they actually put in an x value of 4 here, and the function is just the natural log of x. So if my function is the natural log of x, and I take the derivative, I get 1 over x, and I evaluate it at 4, I get 1/4. Again, you have to recognize this as the definition of the derivative. Okay, so we want the tangent line to have a slope of 1/2. So this is quotient rule. I took the derivative, which is kind of ugly. I simplified it. I set the derivative equal to 1/2, and I found the x values that made that happen. And it asked for what points, so I did use the x values and plugged it back into the original function to find the corresponding y values. Again, if you want the line tangent to have a slope, that's just saying set the derivative equal to 1/2. This one talks about a horizontal asymptote, which just means we're going to let x go to infinity. That's what a horizontal asymptote means. And so if you look at x going to infinity over here, big dog versus big dog, you get 20x squared over 4x squared. The Bill Gates says you don't have to worry about the minus x or the 1, and you get 20 over 4, which is 5. So this one's going to have a horizontal asymptote of 5. This one has a vertical asymptote at 5, but that's not what they asked for. Absolute maximum value of f, right? Anytime you're going to look for extreme values, you're going to want to look at the derivative. So I took a derivative, and then we know that maximums and mins are going to occur at 3 particular pieces, right? We know they're going to occur at endpoints, where the derivative equals 0, and when the derivative doesn't exist. And that's what I did here. I found out that there's an endpoint because the domain for a logarithm is 0. And then I found the derivative is equal to 0 at e, and then I checked those values. It says what's the absolute maximum value of f, so it's looking for the y value. Again, this finds the x values, and you got to plug it back into the function to actually find the y value. And again, it's a maximum here because the derivative is positive and the derivative is negative, so at x equals e, there must be a max. Okay, we want a critical point to occur at a certain x value, and we want to find k that makes that happen. So we want to figure out where the derivative is equaling to 0, or derivative not existing. In this case, it's equal to 0. So I used product rule on g to find g prime. I set g prime equal to 0, and I want it to be 0 when x is 2/3. So I'm just plugging in x of 2/3 into the function and finding k that makes it 0. This exponential is never 0. There's no value, so I didn't really have to worry about that. I really just want to worry about this. Whenever this is 0, of course, that's going to be 0 because you're multiplying. We're going to find the second derivative, so this is like implicit differentiation here. So we're going to take this is a product rule over here, and then just normal here. So this side is the product rule, and then the derivative of 2x is 2, and the derivative of negative y is negative y prime. And then what I did is, if you know the point 3, 0, you can plug that point into this first equation to find the corresponding derivative, because in the end, if you look at this equation, you need to know x, y, y prime, and y double prime. And if you know this, you can find y prime based on x and y, and then you can find y double prime. Okay, we want f prime to be positive. All right, so we want our function to be increasing, and we want f prime to be increasing, which means we want a positive second derivative, which means we want concave up. So we want the function to be concave up and increasing. Looks like right there. Okay. This is basically the mean value. No, this is the intermediate value theorem, and they give us 2 points, and they say, hey man, which of these must be true based on the intermediate value theorem? And it basically says that as long as your function is continuous, every value between 10 and 20 has to be hit at least once. So I guarantee that there is an x value such that f of x equals 13 at least one time. I want the slope of the graph at a single point, and I want it when it crosses the x-axis. So I did have to find out when this crosses the x-axis. I found this x value, and then I just took the derivative of this function at that x value. And again, I used my graphing calculator and Ender to do that. Here, this is the graph of the derivative, and if you can see at the beginning, it looks like the derivative is negative. So if like this is water coming into a barrel, the barrel is leaking water here, gaining water there, and then leaking water here, right? Negative area, positive area, negative area. And so a minimum is going to occur right there. Has to be a minimum there, right? Well, no matter how much water the barrel starts with, it's going to leak right away and get to a minimum. Then it's going to come in more and become a max, and then it's going to leak. A local max, I mean, we really just graphed the derivative, and I found the zeros, and I showed you that the derivative here was positive, and then the derivative is negative. That's got to be the definition of a max, right? If the derivative is positive, the function's increasing, and then the function would be decreasing here, where the derivative would be negative. I want f to be concave down, so I'm looking for a negative second derivative. So I went ahead and graphed f prime, and then I'm looking for a negative slope. A negative slope on f prime is when f double prime would be negative. I want a local max, again, thinking about water going in and out of a bucket. Water's going to be out of a bucket, water's into the bucket, water's out of a bucket. So that's going to be a maximum. Again, this positive area, water's coming in that whole time in terms of a flow rate. Remember, you're looking at the graph of the flow rate, of the derivative. I want f to be concave down, so then I'm looking at the graph. I'm looking at the graph of f double prime. So I just want it to be negative, so I just picked out the negative areas. That one should be pretty easy. I'm not even sure why that's a calculator question. And then this last one, if you look at the slopes, the derivative, right? The derivative is getting smaller, which means a negative second derivative. Then the derivative is getting bigger, positive second derivative. And then here, the derivative is getting smaller, a negative second derivative. So it looks like there's at least 2 points of inflection because the second derivative has 2 different sign changes. Again, you can figure out a sign change of the second derivative by looking at the values of the first derivative. Okay? Hopefully this helps you kind of walk through the 2012 AB derivative questions.